Hello everyone, welcome to this second video of our NLP research playlist where we are going to see in detail about DPO, which is Direct Preference Optimization. The paper is titled as Direct Preference Optimization, Your Language Model is a Secretly Rewarded Model. Okay, so it is one of the great papers which have been released recently. Okay, so the main advantage is that we'll be seeing if it can serve as an alternative for RLHF. Okay, RLHF, if you are wondering, is something which has been used in ChatGPT. Okay, so let's start with what are the sections we'll be seeing in this video. So in this video, we'll be seeing about the abstract, introduction, preliminaries, DPO method, experiments, and conclusion. Okay, and for implementation, we'll be making a separate video because the implementation is kind of longer. Okay, so in previous video of explanation of LoRA, the implementation was done prior as well as the explanation wasn't too long, so we combined both into a single video. But in this, since DPO itself has a lot of contents to discuss about in the research paper, so we'll be seeing the implementation in the next video. Okay, before moving into the abstract, let me say what is the essence of this paper. Okay, so DPO, which has been proposed in this paper, this method is a computationally efficient method which calculates the log probabilities of preferred and dispreferred completions. Okay, so you need not worry about what this essence says. While we complete this video, you'll be understanding, okay, this is what the essence of the paper is. And okay, that line makes sense for me. Okay, so that's how you'll feel once you come to the end of this video. Will be like this method will calculate the log probabilities of preferred and dispreferred completions under a model. Okay, so with a model, like it will calculate this log probabilities and it will optimize its parameters in such a way that it will increase the likelihood of preferred responses and decrease those of dispreferred. Okay, so we need preferred responses, not dispreferred, so that we can align the model with human preferences. What does this mean? I'm just gonna explain in a minute. Where here usually we have LLMs. At sometimes what happens is it won't respond in a way we want. Okay, so to make it respond in a way we want, there are some methods, okay, to have some control over the generation, and DPO is one of the computationally efficient method which does that. That's that task. Okay, so coming into the abstract of the paper, LLMs have a broad knowledge. Okay, so it has been trained with lots of data sets, variety of data sets, right? So it has a large knowledge, but the difficulty comes where we can't control the behavior of its generations. Okay, so if we want it to write a story, it will write in its own way, but to have a control over it, to steer the generation, there are some mechanisms like RLHF. Okay, so that will try to steer the generation as per our preference, but the problem is that RLHF is complex and unstable in nature. RLHF stands for reinforcement learning with human feedback. So this is what has been used in GPT 3.5 as well as GPT 4, which serves as a backend for ChatGPT. Okay. Um, the aim of this paper, which is DPO, is to find a mapping, okay, between the reward function and optimal reward policies. So what is that? So usually you'll have a common reward function as well as there will be some policies. Okay, so what will happen is they will have a separate reward model and it will come in different stages. So here, what happens is they'll try to find a single stage policy based training, okay, so that the model can be optimized to align with the human preferences similar to RLHF. But in RLHF what happens is it will take in multiple steps, but in DPO what will be happening is we'll be aligning the model with human preferences in a single stage, making it very computationally efficient. Okay, now let's see a small introduction of DPO. DPO, which stands for Direct Preference Optimization, is a lightweight and highly performant method to train LLMs on preference datasets without a reward model. That's a very key point. Okay, because in RLHF we'll be separately training a model called reward model. And guys, if you want to know about how ChatGPT was trained, such a framework, how it was trained, just let me know in the comment section. I'll try to make a video on that as well. So coming back, experiments have shown that DPO aligns the model with the preferences better than RLHF. Okay, so they have conducted some series of experiments resulting in showing that direct preference optimization aligns the model with the human preferences better than RLHF based on PPO. Okay, PPO means proximal policy optimization. So now let's see an introduction to the paper. Okay, so they started with the challenges existing, which is that, like we said, LLM has great capabilities because it has trained with large variety of data sets, and the data set will have different goals, skill sets, and priorities. Like there will be question answering, there are some pre-trained tasks as well, right? Next sequence prediction, there is mask language modeling. Okay, there are a lot of tasks which are there, and each requires a different skill set, and each are prioritized in a different way. But what happens is some of the capabilities acquired or some of the skill sets acquired are not desirable. For example, sometimes what happens is the model will know about the common misconceptions which is there among people, but we require that the model should be aware that it is a misconception. It should know, okay, there is a misconception, but it should be aware that it is a misconception. Okay, I hope it makes sense. And coming back to the existing solution, like we said, to control the model generation, there are some mechanisms like RLHF. Okay, so RLHF stands for reinforcement learning with human feedback, which is a method based on reinforcement learning itself, like the name states. It involves creating a reward model based on the preference datasets, and it will utilize that reward model to optimize the SFT model's performance. SFT model is nothing but a supervised fine-tuning model, which is maybe your pre-trained model, or like you can consider your pre-trained model, but usually SFT model will be a model which has been instruction tuned. Okay. Now coming into the problems in RLHF, the problem is that it is very expensive and complex because it involves multiple training loops. First, you need to train an SFT model, then you need to train a reward model, then you need to train the final model, which is optimized by the reward model. Okay, so it will have multiple training loops. So now coming back to the introduction of DPO. DPO has the same objective of reward maximization. See, the point is we need to maximize the reward in a way such that it will align the model to the preferences, right? For this, they'll be using KL divergence constraint. So KL divergence is nothing but it will say how different two entities are. Okay. It is used this KL divergence constraint is also used in RLHF. Okay, so DPO shares the same objective of RLHF, but DPO is very simpler to train and implement. Okay, so DPO updates. What happens is that while DPO update is nothing but a weight updation by using DPO. Okay, it increases the relative log probability of preferred over dispreferred responses. The DPO update will happen in such a way that the probability of preferred will be greater than dispreferred responses. Okay, and since here we are not using a reward model explicitly, we'll still rely on a theoretical preference model called Bradley-Terry model. There are some other models like Patrick Lewis model and all, but in this paper they would have followed a model called Bradley-Terry model, which will help to measure how well the model aligns with the preference datasets. Okay. Finally, a loss function called DPO loss is used for eliminating the need for a reward model, because this loss itself will check how much it is aligning. Okay. Now, before moving into DPO, you need to have a clear understanding of what will happen in RLHF and how the optimization and reward all works, because we'll be eliminating the reward component alone from this pipeline. Okay. So let's see about RLHF. So RLHF occurs in three different phases, where first one is SFT phase. Like I said, we will be fine tuning on a high quality data set like instruction tuning. Okay. And the resultant model will be called as PySFT. Okay. So remember this. In reward modeling phase, which is the second phase, SFT will be prompted with a question and a pair of answers. Okay. So question might be your prompt, or else like, generally you can say like summarize the following or something like that. Okay. Some kind of command also fine. So the pair of answers will be such in such a way that y1 will be preferred and y2 will be dispreferred. Okay. So y1 is greater than y2 while it is coming to preference. Okay. This is provided to PySFT, okay, which is your supervised fine tuning model on a conditional probability of y given x. Okay, it will try to predict the probability of y given an x. So here the preferences, like we said, right, y1 and y2. The researchers didn't know what happened inside the preferences creation. Okay, so just they assume that it would be generated by a latent reward model called r star y comma x. Okay, so this preferences of y1 is greater than y2 is created by a latent reward model called r star y comma x. Okay, so for this preference distribution, the reward model is following Bradley-Terry model in the following way. Okay, so P star, okay, star will be in your uh, suffix superfix. Okay, uh, now P star P star y1 is greater than y2 given an x is your preference distribution, which will be equal to exponential of r star x comma y1 divided by exponential of r star x comma y1 plus exponential of r star x comma y2. This is your equation number one. Okay, like I said, one is your preferred and two is your dispreferred, which means the preferred response reward being exponentiated will be at the top, and will be dividing it with the exponentiated value of preferred as well as dispreferred. Okay, so that's what happens in Bradley-Terry model, which is serving as your equation number one. So usually just remember that we'll be using YW and YL hereafter. Okay, so YW will be your Y1 and YL will be your Y2. YW is greater than YL. Okay, with the data set in this following dictionary way. Okay, so it will be xi, ywi, yli, and xi will be your input, yw will be your preferred response, and yl will be your dispreferred response. I is equal to 1 to n means how many data sets is data points is there, that much data set will be here. Okay, for this a reward model r phi of x comma y can be parameterized under phi. Okay, and then we'll estimate the parameters via maximum likelihood algorithm. Okay, so considering this, when we frame it as a binary classification problem, the negative likelihood loss can be calculated as LR of R phi comma D will be equal to minus E. So here actually if you see, it is not minus E, it is minus expectation. Okay, so expectation of X comma YW comma YL will be approximately will be belonging to the data set. Okay, like you see here XI, YWI, YLI, right? So it is expected the LR phi comma D is expected to be negative log sigmoid of. So sigmoid here they call it as logistic function, but you can also call it as sigmoid, right? So log sigmoid of R phi x comma YW minus R phi x comma YL. So even if you see previously, right, we are always having our preferred first and dispreferred second, because we need to prioritize the preferred first. Okay, so that's why we are calculating r5x comma yw first, the reward of x for completing a response which is similar to the preferred one, subtracted with the response generated similar to uh, dispreferred. Okay, so in simple terms, we'll have a response. Okay, we'll be seeing how much reward is there for it being closer to the preferred response, and how much reward is there for it being close to the dispreferred response. Okay, so in such this way, we'll be calculating the reward, and by that we'll also be getting the negative likelihood loss. Okay, so here the E means expectation. I'll show these equations in paper. Okay, so you need not worry about what will happen. So, but in this video completely, E will be expectation, not a simple variable. Okay, now in LMs, usually this R5 of x comma y, right? Like your reward model parameterized under phi will be your SFT model. Okay, so what will happen is in this SFT model, usually will generate a sequence of tokens, right? So in order to generate a value, we'll be adding a final layer inside the LMs at the last, by which we'll be getting the reward. Okay, so in this, to ensure that there is a low variance in this reward function, there have been some prior works which has happened to normalize the rewards. Okay, such that the expectation of x comma y belongs to D uh, is that the reward of x comma y will be equal to 0 for all x at the beginning. Okay, while it is beginning, the reward for any input and output together will be equal to 0. Now we have seen, like, what will happen in the reward modeling phase. So finally what will happen is we'll have this reward function, sorry, yep, we'll be having this negative likelihood loss function. So by this we'll be using to optimize the model. Okay, so we need to maximize the reward, right? So what we'll be doing is we'll be calculating again, like, the expectation hereafter I'm not going to say about that. Okay, so I'll just call it as expectation of the reward model given an x to predict y. Okay, uh, it should be maximum, so it will be subtracted with a beta parameter. So beta is a hyperparameter to control. Okay, that will have it aside right now. And D, again, D will be somewhat different when you look. This D will be different after beta. There is a D, right? That D will be looking different when we see in the paper. So DKL means KL divergence. Okay, so KL will be in your subscript. So DKL, which is your KL divergence. So we'll be calculating KL divergence for pi theta of y by x, and like the differences between pi theta of y by x and pi ref of y by x. Okay, so by that we'll be calculating a KL divergence, and then we'll try to maximize the reward. Okay, so here pi theta will be your LLM and pi ref will be your reference policy or your model. Okay, your model itself sometimes will be using as your reference model. Okay, so the final reward function will be as, let's say, like, we have a reward function called r of x comma y. It will be r phi of x comma y minus beta log of pi theta y, conditional probability of y by x, and minus log of pi ref of conditional probability of y by x. Okay, so what is there is that we'll be finally calculating the logarithmic value of the reward out of, not the reward, yes, yeah, it is the reward. Okay, so we'll be calculating how far it differs. Okay, so that's the main idea. So here we have this reward, right? R of x comma y. We'll try to maximize this reward by using proximal policy optimization. So that is very important, which we will replace with DPO itself. Okay. So this is your DPO method, where if we usually had a preference rate of YW greater than YL, we'll calculate a maximum likelihood, and based on that we'll train a reward model. Okay. So once that is done, LM policy is your final model. Okay, final LM is your LM policy. So the LM policy will first generate a completion, and it will label the reward. It will optimize the LM policy, and then again the completion will go to reward model. This will happen in a cycle. But here in DPO, what happens is you'll be calculating the maximum likelihood, and in the DPO loss function itself, it will try to optimize it. Okay. So like you see, the reward model is not at all needed here. So it will occur in a single stage. So DPO method, basically why the DPO method is needed. So to solve the challenges of RLHF, only DPO came into the picture. Okay. So what happened was, when RLHF was trained on large scale problems, okay, uh, it was very unstable. Okay. So because what happens is it has multiple reward models, so you can't always say, like, you'll be fine with it. And it is complex as well, like we saw previously. But DPO approach was introduced, okay, such that it will bypass this reward modeling step, and it will optimize the language model directly on the preference data itself. Okay. So here we'll have a loss function. Okay. It will be transformed into loss function over policies. Like I said, we'll be finding a mapping, right? I told you, right? We'll be finding a mapping between optimal policies and reward functions. So what will happen is, the loss function over policies itself will help you bypass this reward modeling step, and that will itself reward you. Okay. But still, we'll need a theoretical preference model, like I said, for which we'll be using Bradley-Terry model for the optimization. Now, first we'll start with deriving the DPO objective. Okay, so here there will be kind of some of the derivation will be only in appendix. Okay, so I'm not gonna cover those. Okay, I won't say about how it will work, because if I cover that, it will again go as a very very long video. So for now, we'll just know what is there. Okay, equation 3, which is this reward function, the optimization problem which we have framed here, right? Like, based on the scale divergence constraint, this is rephrased under a common reward function R. Okay, so pi R of y by x is equal to 1 by z of x, pi ref of y, conditional probability of y by x, and exponential of 1 by beta r of x comma y. Okay, so here it is your equation number 4. Here is where we'll start with deriving the DPO objective. Okay, so here the z of x will be summation of y, pi ref of y by x, exponential of 1 by beta into r of x comma y. Okay, so if you want how this first equation, which is your equation number 4, was derived from equation number 3, again let me know in the comment section. I'll try to make a short video on that as well. Okay, so but basically, what was the idea is that we need to make the problem statement to be made as a general under a the problem statement was to formulate an equation which will optimize the LLM. Okay, so here we are just changing it into a general reward function R. Still, we are considering the KL constraint reward maximization objective. Okay, so we have our equation right now, and once you rearrange this equation with some algebra, okay, in terms of policy pi R, optimal policy pi R. So we have pi R right there. So that is your optimal policy, or else your final model. Okay. And reference policy pi ref and z dot, which is your unknown partition function. Here I have specified partition function, but the partition function will be something which it is unknown. Okay. So it will be r of x comma y, which is equal to beta log of pi r y by y given x by pi ref y given x plus beta log of z x. Okay. So now I'll say how it was reframed. Let's consider this equation, which is number 4. Okay, we have pi r y by x and all, right? But here what we need is reward function x comma y, right? So what we'll do is first accept that exponential of 1 by beta r of x comma y. We'll have this other parameters go to the other side, okay, which will be z of x into pi r y by y given x and pi ref divided by pi ref y given x. Okay, so this is how it will be. So z of x into pi ref y given x by z of x pi r y given x by pi ref y given x. So it will be like that right now. But what happens is now you have this exponential parameter, right? So we can just remove the exponential parameter by multiplying with log. So what will happen is now if you take log on both sides, log of z of x into log of pi r y by y given x by pi ref y given x will be equal to 1 by beta r of x comma y. Now if you multiply this on that side, and we know log of a into b is equal to log of a plus b, you will attain this result of beta log pi r y given x by pi ref y given x plus beta log z of x. Okay, I hope this makes sense. Now we are just calculating our reward function. Okay, so which is our objective in the DPO. The previous equation which we saw, right? When we reparameterized it under a ground truth reward. Okay, so here it is optimal policy. Like we'll see. Like okay, this is our optimal optimal output which we are expecting. Okay, but here optimal model itself will be your ground truth, right? Like the optimal result which you are expecting will be from your ground truth. So we are just rephrasing it everything under reparameterizing everything under r star. Okay, so again now r of x comma y, wherever you see pi r, you can just replace it by pi star. Okay, so it will be not r of x comma y, it is r star x comma y. Sorry for the mistake. So it will be r star of x comma y. Okay, so we saw, right, a Bradley-Terry is there. So Bradley-Terry in the previous equation also we saw, right? Here the equation number 1 is something which is followed by Bradley-Terry. Okay, fortunately what happens is Bradley-Terry depends only on the reward differences. Okay, so this model provides the preferences only based on the differences of rewards. So what we'll be doing is we'll be calculating the rewards for preferred as well as dispreferred r star x comma y1, r star x comma y2, and we'll be subtracting r star x comma y1 minus r star x comma y2. So this is how we'll calculate the reward, and we'll be applying a sigmoid or else the logistic function over it. Okay, so by this we'll be calculating the preference distribution. So now we have this one, right? And we have a preference distribution for the reward function. We have it in the previous equation itself, r star. Like I said, there was a mistake. So now substituting this r star x comma y, which is on top in the second equation in this page, will be attaining the following result, which is in this page. Which is in this image. Okay, so p star of y1 is greater than y2 given x will be equal to 1 by 1 plus exponential of beta log pi star y2 by x by pi ref y2 by x minus beta log of pi star y1 by x by pi ref y1 by x. Okay, so this is how the statement will frame. Again, given there, right? You can refer Appendix 6 for how this conversion happened. It will be simple mathematical calculation, not complex any integration or something like that. It will be just common algebra. Okay. Finally, we'll be having this loss function. Okay, so which is our objective of this DPO. So the DPO loss will be equal to, here you can see, right, the E is somewhat different. So that is called expectation. Uh, the expectation of loss will be log sigmoid of beta log pi theta yw given x by pi ref yw given x minus beta log of pi theta yl given x by pi ref yl given x. Okay, so this is how we'll calculate our loss function. So this is how we'll have our DPO loss. So in this, if you see, everywhere we are giving importance to the preferred response first, and then next we are having the dispreferred response. Okay, so if you have some um, like dispreferred thing, this loss will be very bigger. Okay, and if you have preferred responses, the loss will be smaller. Okay, so that is the aim of this objective. Okay, it will try to find how much the model aligns with the preferences by using this loss function itself. Okay, thus by using this loss function we'll be bypassing the reward modeling step. Okay, now coming on to the update function, which is very important. Okay, so usually the gradient of this loss function LDPO, okay, what it will do is it will increase the likelihood of preferred responses and it will decrease the likelihood of dispreferred responses. That we saw here itself, right? So that is what is happening here also. Okay, it is increasing the likelihood of preferred and then subtracted by it is decreasing, right? And before that we have this reward function being subtracted, right? Like we saw it here, I guess. Yeah, here it is. The preference distribution, which is sigmoid of r star x comma y1. Okay, so that preference distribution will be given before this value. Okay, you will get the likelihood, right, to penalize it and give some rewards or else provide some punishments, which is the idea of reinforcement learning. Okay, here we have this preference distribution. Okay, so this is how the updation will be happening. So the likelihood is increased or decreased based on the responses and the magnitude of reward or else punishment. Here there is nothing called punishment, there is only reward. Okay, the negative magnitude or positive magnitude is defined by this preference distribution weight. Okay, so here r cap theta of x comma y will be equal to beta log of pi theta y given x by pi ref y given x. Okay, so yep, that will be our final DPO reward function. Okay, so when we are coming into experiments, before going into that, guys, if you have any doubt, I know this is a complex paper and in the mathematical part I'm not going into it very deep because it will have a lot of calculations. I'm just giving an overall view of what is happening and I'm just trying to explain basically what is the idea of DPO. So if you like this video, just click the like button and only 35% of my viewers are subscribed, and if you have not subscribed, please consider subscribing the video. Okay, in this playlist I've planned to make a lot of videos and there are some other good playlists as well, which you can check in the channel playlist section if you are interested. Okay, and share this kind of video with your friends because this paper, especially DPO, is I feel gonna go places. Okay, like it will be talked a lot because till now why it has been talked about is that the implementation was not there, but recently the implementation also has came. By this I feel there will be a lot of DPO models which we'll be seeing hereafter. Okay, and if you have any doubts in this DPO, just come and ask me personally also, it's fine, or else let me know in the comment section, come and ask in the Telegram group. The link will be in the description. Okay, that is also fine. And yeah, you can increase your knowledge in this DPO. Okay, so cool. We'll go with tasks first. So in this, they experimented with three tasks for evaluation, which is control sentiment generation, summarization, and singleton dialog generation. I'll say what happens in that. Okay. So in control sentiment generation, what they done was they created a preference dataset based on a pre-trained sentiment model. Okay, where the model is ought to generate a movie review. Okay, given a movie prefix like the movie was. Okay, I'll be having it as a prefix, and it should generate a movie review which is in positive nature. Okay, and again to check if it is positive or not, we'll be using the pre-trained model for evaluation. Okay, so this is coming on to control sentiment generation. For summarization, they have taken a preference dataset for summarization itself. Okay, from a person which I'll show in the research paper. I'm just not getting the name by now. And based on that dataset, they are training the model to align to the preferences. Okay, and for evaluation, they have used GPT-4 and KL divergence. Okay, so similarly, singleton dialog generation also was happened, but here the preferences was not there, so they trained an off the shelf LM. Okay, and then like they used that as a SFT model, and then based on that they made the preference model. Okay, so this is what they done in each of the tasks. And like I said, for evaluation they used scale divergence and GPT-4, and some other methods also was used for evaluation where like they done zero shot prompting with GPT-J for summarization, and two shot prompting with PyTR 2.8 billion model for this singleton dialog task. Okay, so this is how they did some experiments. And after conducting a series of experiments with KL divergence value belonging to 3, 6, 9, and 12 for proximal policy optimization, and beta belonging to 0.05, 0.1, and 1.5. Similarly, alpha parameters are also given for DPO. Okay, so when they conducted experiments like this, it was clearly shown that DPO performs way better than PPO. Okay, it achieved the highest reward with low KL divergence. So usually you will need KL divergence to be very low. Okay, because you need to find the differences between the optimal one and your generation. Okay, so if you are close to optimal, then your KL divergence value will be very less. So we need to gain the highest reward with low KL divergence, which was achieved by DPO better than PPO. Okay, but consider guys, this DPO is a computationally efficient method. That is very important. Okay, it outperformed all the methods in RLHF, it seems, especially they considered PPO. Okay, so for coming on to the conclusion, DPO is a simple training paradigm, okay, for training LLMs or LMs even, because it's not just restricted to LLMs. That's why they gave it as LM. Okay, so even for language models, if you want to align it with your preference, let's say GPT-2 is a language model. It's not large language model. It is slightly smaller, right? So even you can use DPO for that kind of model as well. Okay, so this will be an easy, simple training method, okay, for training LMs without RL, but to align with the preferences, because it will be steered just by a simple cross entropy loss. Okay, so in that loss function itself, we made it as a loss function over policies, right? So by that you'll understand that. Okay, with the loss function itself, we aligned it with the preferences and we steered the generation, which was the aim, right? Like it was the aim of RLHF, but it was very complex and unstable. But this is a stable approach and it is very simple, right? So that is a key conclusion from this paper. And some of the advantages is that DPO performs similar or better than existing RLHF algorithms, okay, including RLHF based on DPO. Sorry, not DPO, it's PPO. Okay, I made a spelling mistake there. When I'm giving the slide, it will be changed, so you need not be confused. Okay, so even based on PPO, there are RLHF algorithms, and that is outperformed by DPO. Okay, but the key point is that DPO also reduces the barrier for training. Okay, so usually the main barrier is that we'll have computation issues, and here it doesn't matter, right? You are not training a reward model, which means you don't need that kind of a computation. So to simultaneously run a reward model also, you'll need some uh, yeah, sorry for the misclicking. Okay. Yep. So if you see, like, we'll be having very less computation. So that is what is the conclusion of the DPO. Okay. So you can achieve the same or better results than RLHF, but with minimal computation power. How much minimal is that? We have trained DPO again in Collab itself. The two in free version. Okay. So I'll show you what you can expect in the next video. Okay, so a model which was generating like this, like, for a given question as should you buy a case to protect your cell phone, it was generating some random Java program. Okay, this was fine tuned again with DPO to make responses like this. I would like to help you to protect your phone, like that. It is there. Okay, it was not trained for longer period as usual. This is for tutorial purposes, right? I didn't train it for longer period, but and also the samples was very less. But I'm surely confident that with longer training time and with larger sample, you can gain great results. But still, I wouldn't say this is worst, because see, a model which was just trained to generate code was generating chat which was making some sense. Okay, so DPO did work well. So this is how you can compare it. Okay, that's how good DPO is. With I think this model was trained in 20 minutes if I'm not wrong, 15 to 20 minutes. Okay, so you can see it was very short time. Okay, and also this is a quantized model. So I'll say like DPO is top notch. Okay, now seeing on this paper we saw the abstract section, right? And like you see here, we have related work which we didn't go in detail. Okay, preliminaries we saw about it, and deep direct preference optimization we saw it, right? Theoretical analysis of DPO, they would have seen about, like, the equation, how it will work under different situation. They would have made some theorems based on that. And if you are interested, go through the experiment section. It was very useful. Like, it had great knowledge in that. There were some interesting results which have been encapsulated in this experiment section, but I covered only the 2 to 3 things which will be needed for us. Okay, and uh, here I told we had evaluated it under GPT-4, right? But the point was to align with human preferences. So it would have been great if human evaluated it, right? But with a test on n respondents, right? Humans even agreed that GPT-4 almost agrees with them, or else even GPT-4 response is sometimes better than human. That's what a test has been given. Okay, and we saw the discussion. And coming on to the future work, that is something which we need to see here. Okay, so here the main one is you will be seeing here. When you have something unlabeled, okay, so here what happens is our model itself will train, and with the same reference model it will optimize itself. When I'm showing the code part, you will understand it. Okay, again I'll show a small tease of what will be the implementation code. Okay, but before that, the theoretical code, how it will be converted, I'll show in this video itself. So when you have something out of the distribution with an explicit reward model, okay, so you'll be able to optimize it. But self-rewarding model, that is a case study which needs to be seen. That is an important future work they had discussed about, and also they had trained models only with maximum of 6 billion, and they said like they will try to evaluate it with bigger models. Okay, and like I said, here there is the derivation, right? Even in this derivation, some steps were skipped actually. So if you want, you can check this out. Like I said, if you are in need of knowing about this mathematical equation, like you want me to derive in live, let me know. I'll make a video on that as well. And here is how you can implement this in PyTorch. Very simple. You'll have the log probabilities from the reference model, and policy will be your normal model. Okay, and preferred completion and dispreferred completion. You'll have all of those, by which you'll have your preferred log responses, dispreferred log responses from your model as well as from the reference model. Once this is calculated, you will be subtracting preferred from dispreferred, and based on that, we'll be multiplying the beta parameter and we'll have a log sigmoid or on top of it, and we'll be having it as a negative value. Okay, so this is what we saw there, right, in our last function. So just give me a minute, I'll show you. Here it is. Okay, so here is your log ratios. Okay, and you're just subtracting it, right? Beta star. Okay, so you can have it as another bracket here. And finally, we are calculating the log sigmoid. Okay, so this is what has been happening in this code. Okay, and for this rewards beta star pi log piece, which is here. Where was it? Here. Okay, which is your preferred, sorry, log probabilities from your model, SFT model, minus log probabilities of your reference model, and will be multiplying with beta parameter. Okay, so that you can see it here. Log probabilities of your policy model by log probability of your reference model. Okay, and right, log of a by b will be log of a minus log of b. So this is how it has been implemented in Python as well. Simple implementation, guys, but to implement it with a framework, thanks to Hugging Face again. Okay, they create an amazing library called TRL. In this recently, they have created DPO as well, support for DPO as well, and I'll show you how it happened for us. Like I'll also show you the code. I'll just give maybe kind of a teaser of what we can see in the next video. So this is the trainer which we'll be using, and here you can see what all are there. We have inputs concatenated. Okay, we'll be concatenating chosen, rejected, and all will be concatenated to a single one. Okay, it will be separated as well again. And we have our DPO loss function. We have the log piece. We need to get the log piece, right? So that also there is a function on that. Okay, and here we have this compute loss function from which we'll be calculating the DPO loss. Okay, so yep, here is the implementation of DPO. Okay, so here also the DPO loss, if you see, it is same as what we saw there. Okay, I hope this is cool. Okay, and for rewards, here what they did is they calculated the chosen reward as well as the rejected rewards. Okay, for chosen reward they subtracted chosen policy log probabilities minus reference for chosen log probabilities, and similarly they did it for rejected rewards as well. Okay, so this is how it is implemented, and the trainer we'll see about this trainer and all in a separate video. Okay, because I'm planning a playlist on TRL library itself. Like you can see here, we have proximal policy optimization trainer, PPO, as well as there is a reward trainer, there is SFT trainer. Okay, I will make a separate playlist on this, and if this is the most thing which you are interested in right now, let me know. I'll maybe even make a live session, a detailed live session, okay? Maybe 2 or 3 days continuously, and we'll see about all the trainers, okay? And we'll see like how it is happening. I'll see in live itself, okay? So it will be kind of an interactive session. I won't even learn it anything in prior, okay? So that we can have an interactive session and learn together. And if you are interested in something like that, let me know, okay? So this is the library which we'll be using, okay? And again, I'm going to show you the code as well. Open notebook. Yep. I'll be explaining the code separately. Okay, so here also you can see we have three files, right? Like, we have SFT, we have DPO, and then followed by inference file. Okay, so here is our LoRA. We have it. Okay, and here you can see we have only 5,500 steps, and batch size was 2, which means we have trained it only on 1,000 samples. Okay, for 1,000 samples to get this kind of result. See here, guys, it's amazing actually. The training loss is also decreasing from 5.9, it became 5.1, and the validation also it decreased from 6.5 to 5.6. That is pretty good actually. Okay, so um, that's actually pretty great. And also, if you see the accuracy of the reward rate, it was constantly improving, which means it was going in a correct direction. Okay, so the rewards direction, if you see, right, it is in negative in nature, which means it should decrease. Because if it is going -1, -2, it means it is performing very worst, right? So here it is decreasing from -1.818 to 0.84, which means it is doing better. And if we had trained it for a longer time, it would have given some better results. Okay, so this is not an error. Okay, what happened was something related to save, and it is not a problem now. It will work. Okay. So this will be our next video. Okay, so I'll upload this video, which is on implementation tomorrow itself. So make yourself available tomorrow to see this video. And guys, really, I'm saying it will be amazing to see how much this performs very well. Like, this DPO is literally so good. Okay. So as much as I like about the contents on LoRA, okay, LoRA helped us to train large language models, right? So this is as good as uh, LoRA, okay, but still this is not been talked highly yet, but I expect people to talk about this highly later. Okay, so that's it for this video, guys. I'll see you all in the next video with the implementation of DPO. Until then, cheers.